Okay, so the next one we're going to take a look at are forces. This one's an important one. As we've seen, forces, we first started off with some of the regular mechanics stuff, and then we found that as we learned new physics, we kept coming back to the forces. They showed up again when we were dealing with fluid mechanics. They showed up again when we started dealing with electricity and magnetism. Forces have a tendency of showing up all over the place. This is one of the key things that you want to make certain that you're comfortable with and able to apply whenever you need to. Now, of course, the important equations, the absolute most important one is going to be Newton's second law. And that says the sum of our forces equals the mass times the acceleration of the object. All right? So, it is absolutely important. I know that we get in the habit of saying simply F equals ma, but don't forget that summation, because that's fundamentally important. We have to look at all the forces acting on an object. And the other thing to pay attention to are the vectors. These guys have direction. As you remember, I pointed out when we add vectors, we have to split them up into what's happening in the x. So we'll do sum of forces in the x equals our mass times our acceleration in the x. And we'll also split it into the y. Sum of forces in the y equals mass times our acceleration in the y. If you have more dimensions than that, maybe a z dimension, then you would just add one more where it's what's going on in the z dimension. We'll stick with just three-dimensional space for now. This is fundamentally one of the most important equations to have familiarity with and know how to apply at the drop of a hat for all of physics. Next equation. Some common forces that you're going to have to deal with. The one we dealt with in class was kinetic friction. It was equal to mu sub k, where this is the coefficient of friction, times our normal force, the force pushing the two surfaces together. And mu sub k described basically how rough our surface was. Now, similar to this, in fact, when you see it on some of the exams, it's provided where it's the inequality, where the force of, that includes static friction, where this was static friction instead, where the surfaces aren't moving, is less than or equal to, the most it can give is the coefficient of static friction times our normal force. Something to keep track of. But the one that I find a bit more useful is this guy, the kinetic friction. Another common one that shows up, force of a spring equals negative k delta x. Don't forget that negative. Remember, the negative there says that if I push this way on the spring, the force I feel is pushing me back. Or if I pull this way, stretching it out, I pull this way, that's my delta x, my force is actually pulling it the opposite direction. There's always this opposition. If I move one way, the spring is going to try and push me back to its natural length, or pull me back. That negative tells you that. It's always in the opposite direction of how you move it. And of course, one of the most important ones, I probably should have moved this up higher, the force of gravity near the surface of the Earth. Now for my students, they're used to the fact that I use F sub little g, and that tells us the force of gravity near the surface of the Earth, which is equal to our weight. A lot of times people will use just W, but I prefer the more descriptive approach this way. We'll have the mass of the object times the local acceleration due to gravity. Now the nice thing about this is, while I mentioned that it's near the surface of the Earth, we could also have this applied to the surface of Mars or the Moon. We would have the force of gravity there would be equal to the mass of the object times the local acceleration due to gravity, which on Mars I think was 3.6 meters per second squared, something like that. And on the Moon it's 1.67 or some such. Anyway, you can look those up. The important thing is this applies anywhere where your gravitational field is pretty well constant. And so, for the most part, when you're near a very large object like a planet. Okay? These are kind of the main force equations that you'll use, at least for regular Newtonian mechanics. As we go through specific sections of physics, things like electricity and magnetism, we'll have other forces that we add to this. But these are kind of the mainstays that show up when you first deal with the initial forces. All right, some important things to remember about forces. Absolute most fundamental thing is free body diagrams. Be familiar with how to use a free body diagram. This is where you take a dot to represent your object, and you identify what forces are acting on it. Well, if I've got a book sitting on a table, then I'm going to have gravity. The force of gravity, mg, pulling it down, and I'm going to have the normal force from the table holding it up. Now maybe I start pushing on it from the side. There's an applied force, or a force of push. So it's however you want to mark it, feel free to mark it however you'd like, but make certain that you can understand it, and to the best of your ability, you use something kind of normal here, like, say, F sub n, or a capital N for normal force. If you call this squiggly face, then a lot of people are going to have trouble identifying exactly what force it is. And don't be afraid to mark that force, or label it somehow. Maybe not necessarily with an arrow, because that can be confusing, but say something like push, something like that. All right, so if you think that anyone won't understand what force you're trying to identify. And then if I'm trying to push the book but it's not moving, I might have the force of static friction, which will look very similar to this, except that inequality, holding it in place. Or maybe I am pushing it at a constant velocity, and this is kinetic friction, and we'll find that it's equal and opposite. Now, in the end, I use this, my free body diagram, so I can keep track of all of my forces. And that allows me to come back up here and apply Newton's second law. In fact, anytime you find yourself dealing with a free body diagram for one reason or another, you're pretty much guaranteed that your next step after drawing those in is to apply Newton's second law. The entire point of a free body diagram is so that you can see all of your forces very quickly and very easily. So if I were to apply this, I would find my sum of forces in the x. In this case is my applied force, my pushing force, minus, say, my force of static friction. That's going to be equal to my mass times my acceleration in the x. Since this is static, that means that it's not really moving, and my acceleration is 0 meters per second squared. If this were kinetic instead, and I had some acceleration, I could put that in and I could still solve them. It's all about setting up your Newton's second law and then filling in what you need. Okay? If it's in equilibrium, where our forces cancel each other out, then our acceleration is going to be equal to 0. I would do the same thing in the y direction. Equals my normal force minus mg. Again, I mentioned in one of the other videos that when we use this, we're going to use just the acceleration due to gravity, always the positive number when we're doing this, because the minus, our direction, is already taken care of in our sum of forces. Equals mass times acceleration in the y, which often when you have something sitting on a table like that, your acceleration in the y will be 0 meters per second squared. Always ask yourself, is it accelerating downward or upward, maybe like a Ferris wheel? Then you might end up with an actual acceleration, but usually it's often going to be 0. Just go through and see what the problem gives you, fill them in with Newton's second law. Okay? Forces, again, are one of the most fundamental things that you want to make certain that you are comfortable with physics.